Hi everyone, my name is Wei Ji, and in this tutorial, I'm going to teach you how to convert a LiDAR point cloud into a 3D digital surface elevation model. So let's go. To start off, we're going to import a few Python libraries. We'll be using LastPy to read in LiDAR last files. We'll be using pandas to read in XYZ data. So have our data in this XYZ table format. Obviously, we'll be using PyGMT to do our figure plotting and also some data processing. And lastly, we'll be using real X-ray and X-ray. So these are just to export our final digital surface elevation model into a GeoTIFF format. And first thing first, we still need to get some LiDAR data. And for this example, we'll be using data over Wellington, which is the capital city of New Zealand, somewhere I've lived in for a few years. They've had a lot of good LiDAR data products. So you can click on these links to find out more. This is published under a Creative Commons license. And LINZ, which is Land Information New Zealand, the government agency, the geospatial government agency in New Zealand, does a lot of open data work. So be sure to check out these links. And I also encourage you to check out this blog post where this tutorial is based on, from points to pixels. Do check that out if you have time. And without further ado, let's find out how we can download this LiDAR data. So we'll be using the function called PyGMT which to download our LiDAR data. What PyGMT which does is you can pass it a file name from, say, a URL. And for that, I'm just going to give it this open topography URL where the LiDAR data is located at. And PyGMT which has this download function, download parameter, where if you do like a download equal true, this will download the file to locally, and so this file now will exist in our file browser. If we refresh that, you see, okay, we've got a new LiDAR file. It's about 32 megabytes. Yep. And so this string, we want to save the string for later. So we'll store this string in a variable called last file. And that way we can use it to load know this file path later. And to load our last data, we'll be using LastPy. So lastpy.read. We'll need to give it a source. The source being the path to our last file. We call this last data. So if we do that, we can load our last file into this last data object. So this has like about 7 million points and a few like extra things. So last data is this object is a little bit hard to work with. So what we'll do is we'll have this data, we'll put this data into a pandas data frame instead. So we just do a pandas data frame. So with a pandas data frame, you need to give it some data. So our data, we can use a dictionary to put in the data. So we'll have a few columns. We have an X column where the last data, we get the last data, X data. And we need to do this skilled array thing because the last data comes in this skilled format to conserve space. So we need to use skilled array to scale it back into proper physical units, where X and Y are the geographical coordinates and Z here is the elevation value. Skilled array. Yep. And so these are the first three columns. For the fourth column, we'll have a classification column. And this is, so every point in the LiDAR point cloud can have a classification associated with it. So it can be classified as ground, as water, as a noise point, etc. So this is just a useful way for us to know what each point actually means. So here as you can see, we have our X and Y coordinates. These are in a New Zealand transverse Mercator projection coordinate system. We have our Z values, which are elevation above sea level. So there are a few negative values here. Our area of interest is actually part of it is over the beach, the coastal area. So there are like a few negative elevation values, and then the classification here is just our the LiDAR point classification for each individual point. Okay, now that we have our data in this DF pandas data frame, we can a good thing to have is our bounding box region, so which will be useful for our plotting our maps later. So to get a nice bounding box region, so basically the extent, the x min, x max, y min, and y max, we can use PyGMT.info to do that. So just getting information about our data tables. So we give it our data frame. We just need to use the x and y columns to get the min and max values of that. We set a spacing of 1 meter because we'll be processing our grid into a 1 meter resolution grid resolution DSM later. And this will give us a list where we have the min and max x values corresponding to this first column, and the min and max values of the second y column. Okay, next we can also print some summary statistics. So as I said before, there are about 7 million points within this data frame. We can also look at more descriptive statistics of this pandas data frame. So as you can see, so we have about 7 million points, and our mean exact elevation is about 6.5 e, so about 65 meters above sea level. So this is just a quick way to look at inspect our data, that make sure that it looks okay. Next, we're gonna do a quick plot for the point cloud on the 2D map. We'll do a quick filter first. We'll select every 20th points because 7 million points is will be a bit slow to plot. So we're just going to do df.iloc and select every 20th point. So instead of 7 million points, we now have 360 plus points instead. So this will be a bit easier to plot. To plot our point cloud, as usual, we'll need to start a PyGMT.figure instance. PyGMT.figure. And we'll do a base map. We just use the default map frame for this. Frame equal true. We'll set a region. So the region we got before, and also a projection. So in this case, we'll just use a linear projection for 1 to 5000 scale. And this will give us a base map. So this right now is just a blank base map, but we can add a few things to it. So we can do, let's make a color palette table first. So we use the Bukavu color palette table and set the min and the max range of this color palette to be the minimum elevation value and the maximum elevation value. So df.set.min and .max. With that, we can then use fig.plot to plot our filtered x values, our y values, y equal df filter.y, and we're going to color the points by the exact elevation value. We'll set a style. So style just being how we want the points to be rendered. In this case, we'll use C circle for circle. We'll set a 0.03 centimeter circle. And in order to use this CPT, this color palette table, we need to use CMap equal true. Okay, so that's our fig.plot call, and this will take a while to plot because it's quite a few points. Yeah, so now we have our point cloud plotted on a 2D map. So there are like some boats sort of on the top left corner where the harbor is located, and then towards the southeast you can see the elevation at sort of higher peaks. So actually the colors, you don't actually know what the colors mean, right? So let's do a color bar so that you know what I'm talking about. So if we do fig.colorbar and let's set our position to be capital justified to the middle right of the plot, we'll have a frame as well. And I'm just gonna copy this. So our frame would be, we're gonna set some labels for our frame. So elevation, this is, the colors will be stand for elevation, and the elevation is in units plus L meters. Okay, so now we'll have a color bar on the right. And it will be easier for you to understand what colors mean. Okay, so blue colors are sort of water, and then the higher elevations from dark green to this orange white is higher parts of the topography there. Okay, so this is our point cloud. Next, we're going to turn this into a digital surface elevation model. To do that, we'll do a few pre-processing steps first. One step we'll do is to remove any noisy points. So noisy points in LiDAR, the high noise points are classified as 18. So we're just going to select using df.query. You can, this is like an SQL query like syntax. With pandas data frame, we can select any values where the classification is not equals to 18, and that will reduce the number of noisy points we have in our, when we do the grading later. So now there will be less data points. So before we had a noise point which was 18, but now in this new data frame, we have no points with a classification of 18. So if we remove the high noise points right now. Next, another pre-processing step we'll be doing is to run this through a block median function. So for a digital surface elevation model, we should be picking the highest elevation within like a grid spacing. So what block median does, I'll show you in a minute. PyGMT.block median. What this does is that it takes the, by default, it takes the median elevation value within each grid cell. So the grid cell is something we have to set. Let's say we set it to 1 meter. So for every 1 meter grid cell, it would, by default, it would take the median elevation within that grid cell. So let's say you have like 1,000 points within a 1 meter grid. It would take the median elevation of that. For a digital surface elevation model, though, we want it to select the highest elevation instead. So we'll use like a quantile. So there is a t parameter where we can set the quantile. I'll show you what I mean in a minute. So first we'll need to pass in our data. And this is our XYZ data in the pandas data frame, the DF. Like this. We'll set our quantile. So in this case, we'll be using 0.99. So this is i.e. the highest point within each grid cell. The grid cells, the grid spacing is defined using the spacing parameter. So we will set a 1 meter grid spacing, and the plus e just means exactly 1 meter. Because GMT, if you don't use the plus e, it might output a grid spacing of something like 1.000 something instead of exactly 1. So if you do the plus e, it will force it to be exactly 1 meter. Next, we also need to set a region, which is just the region we had before. Okay, and and this will output into a data frame. So let's call this data frame df trim. And you can inspect what this looks like later. Okay, so from about 7 million points, we're now down to about 300,000 points, where so we only have 1 point for every 1 meter grid cell right now. Okay, now that we have this on block median grid, we're gonna turn it into a proper X-ray data array grid. To do that, we'll be using a function called PyGMT.surface. So what PyGMT.surface does is this does a adjustable continuous curvature spline. So just a spline function in 2D. PyGMT.surface, we're going to give it our trim data frame. We'll pass in the data x, y, and z variables. Yes, trim.y, and also z. equal df trimmed c. We'll also need to set a grid spacing as usual. So we'll be using an exactly 1 meter grid spacing. We need to set a region, just the region we had before. And this thing, this tension factor parameter, this is also important. So for steep topography, it's a good value to use is about 0.35. So in our case, because our point cloud, there are like some buildings on there, and as you know, buildings have like steep walls. So a tension factor of 0.35 is a good value to choose. You can also, for like more gently undulating topography, you can use a lower value like tension factor of 0.25 instead. So this is a number you can sort of play around with, but let's go with 0.35 for now. And let's run this. You can safely ignore the warnings. It's just saying there are like some points which it's going to ignore, but that's okay. And after that, we can look at our grid output using we'll just print the grid here. So if we look at the x and y values, now you'll see that for we have a 1 meter spacing grid. So every 1 meter, the x values are for every 1 meter, same for the y values. And for each x and y value, we have elevation value associated with it. So here it is like 32 meters above sea level. There are like some minus negative values, which are areas located over the ocean. This would have like a negative elevation value. Next, we'll do a quick plot of the grid just to show you how it looks like. So we'll start a new figure. Let's call it fig.2. And like this, we'll have a base map, just a simple base map with the default map frame, the region we used before, and the same projection x1 to 5000. And we'll be using fig.grdimage to plot our grid. So we'll just give it grid equals to grid. Let's use a color map as well. So we'll use makecpt to set our color palette table, where we'll use the same Bukavu color map. And let's say we want elevation just from -10 meters to 200 meters. Okay. And we can do a fig2.show. Oh wait, and let's add a color bar as well. Color bar, so just the same color bar. I'm gonna copy the parameters before from our original plot. So now we have just a 2D plot of the grid we produced. So you can make out sort of like some buildings here, and also along here, like almost in like a terrace fashion. So people in Wellington, they like to build on the hill for some reason. And we're seeing that in our digital surface elevation model. Okay, next comes the fun part. So we'll be plotting this flat 2D map. We'll be turning this into a proper 3D map. To do that, we'll be using a function called grdView or grid view. So let's start a new figure called fig3. PyGMT.figure. And we'll be using the grdView function. So grdView, it just creates a 3D perspective image from the grid. So we need to give it our grid like this. We'll give it a color map. So just the same Bukavu color map, scientific color map. We'll need to set a surface type. So we just use S for a regular surface plot. And the key thing you want to play with is this perspective parameter. So what perspective takes is, it takes two values. The first one is the azimuth bearing. So in this case, azimuth being 0 being north, 90 being east, 180 being south, and 270 being west. So let's say if we want to do northwest, we'll use azimuth of 315. And the second value in perspective you want to set is the elevation angle. And the elevation where 0 is if you're looking from directly across the horizon, and 90 is if you're looking from LiDAR, from the top down. So let's say we want to look at it at a 30 degrees angle from the horizon. Okay, so once we've set our perspective, another thing you want to set is the vertical exaggeration factor. So this is just something you have to play with. I found that a value of 0.02 works well here. So let's just go with that. And then finally, we'll make sure to show our plot. And this is how it would look like. Let's give it a few more seconds. Yep. Now we have our 3D plot. So we have the harbor, Wellington Harbor, sort of at the bottom here, and on the top is Mount Victoria. You can sort of make out a few buildings in like a terrace pattern around this hill as well. Okay, next, we're gonna expand on this plot a little bit more. So I'll just copy the code here and paste it here. To make it look a bit nicer, we're gonna add a few more things. We're gonna add hue shading using, and this can be done just with shading equal true. This gives it the default hue shading parameters. And then we will need to we can set a map frame as well. So with a 3D map frame, you have a few things you can configure. The first thing is like the X. So there are the 3 axes, X, Y, and Z. So you can say for the X-axis, I want to label it as easting. For the Y-axis, I want to label it as northing. For the Z-axis, I want to say, okay, let's label it plus L, label elevation in meters. And for this plot, we can also set a title. So this plot is over Oriental Bay in Wellington. So let's just do plus T Oriental Bay Wellington. And then we can have it show it like this. Okay, give it a few more seconds, and voila, here we go. So now we have our X, Y, and Z labels to make so people know what these axes are, and we've got some hue shading to make so the buildings actually stand out a bit more now along Mount Victoria, and this is over Oriental Bay. So we've got a title for this plot as well. Okay, and this is pretty much it. So last thing is we want to save our figures to a proper file. So we can use fig.savefig, and we can just give it our file name. So say our first figure was the LiDAR point cloud. So let's go Wellington 1D LiDAR. And this will save it to here. So if we refresh that, you see we've saved our figures. We can also save our other figures. So we've got Fig2 and Fig3 as well. So our DSM in 2D and also in 3D. So we can save that to a PNG as well. And that will pop up there, 2D and 3D. So we've got our figures saved to a file, and you can download them later if you want. Okay. And the final thing is our digital surface elevation model in grid. So this grid we have, we can use real X-ray. Real X-ray has a real.to raster function where we can save it to a specific raster path. So let's just save, let's just call it DSM of Wellington.diff. And this will save it to this file here. Okay, and we can inspect that, let's say with GDL info, DSM of Wellington. So we can see, okay, so this is a proper GeoTIFF that we've saved it to. And that's it. This is basically the tutorial on how to convert a LiDAR point cloud into a 3D digital surface elevation model. And as a bonus, you can also play around with this example, which is over Queenstown, New Zealand, another popular tourist spot in New Zealand. So I've given you some files. You can paste it into this code cell and then run it through the same workflow I showed you just now. And hopefully you can get some 3D plots done as well. And that's pretty much it. There are a few other examples, tutorials, and gallery examples you can check out here. We have a forum over here, which you can check out if you have any specific questions on, or if you need help with anything. And do check out our GitHub repo as well if you have any feature requests or bug reports. Thank you very much for listening, and we'll see you next time.